Good day. In this lecture video, I'm going to discuss solution to sample problem number 4 in lecture 4 about EMF, internal resistance, and terminal voltage. So before continuing, it is highly encouraged to review or read in advance some of the concepts in lecture 5. Okay? So in this problem, we have two batteries, okay, with the EMF of 6 volts and internal resistance of 0.25 ohm, and another battery with an EMF of 12 volts and internal resistance of 0.5 ohm are connected series opposing. Okay? We'll talk about that shortly. An external resistance of 5.25 ohm is connected across their terminals. To determine, okay, the total supply current, then the terminal voltages of the first and second batteries, and then the terminal voltage of two batteries in series. Okay? So first step, we identify the given quantities. Okay? So here we have again two batteries with their EMFs and corresponding internal resistances, and also the given external resistance. So our target variables are given here. Okay? The total supply current, okay, should be let's first determine the total supply current, which will be used to solve for the terminal voltages of the batteries. So here is a rough sketch of the situation. So it will be very helpful to draw at least rough sketch in order to better understand the problem and to be easier for you to solve the problem. So before executing our solution, so first let's discuss the term series opposing. Okay? And given in this figure, or in series opposing, the connection of the batteries are as such. Okay? So to understand series opposing, okay, that is given in this connection of the two batteries, first we only consider one battery at a time. Okay? So for example, let's only consider the first battery connected directly to the external resistance. So in this case, the direction of the current will be dictated by the EMF. So in this case, it will be clockwise. Okay. Now we only consider the second battery and connect point B directly to the external resistance. In that case, the current will be in the counterclockwise direction. Now, if we connect the batteries as shown, okay, so the first battery will try to force current in the clockwise direction, and the second battery will force the current direction in the counterclockwise direction. So eventually, one of them will prevail. And intuitively, the battery with the higher EMF will dictate the direction of the current. So in this case, it will be counterclockwise as shown in the label here. Okay? So, and since E2 is greater, or the EMF2 is greater than EMF1, then the direction the current will be counterclockwise in this example. And so with the current direction determined, okay, so when we analyze the first battery, the current enters the positive terminal of the battery and leaves the negative terminal of the battery. So this implies that the first battery is being charged. Okay? And for the second battery, the current leaves the positive terminal and enters its negative terminal. So that implies discharging. Okay? Meaning, the second battery is supplying power to the rest of the circuit. Therefore, so we have the expressions for the terminal voltages of the batteries. So the terminal voltage of the first battery is equal to its EMF plus, take note, plus the current times its internal resistance. Because, again, the first battery is being charged. So for the second battery, okay, so its terminal voltage will be equal to its EMF minus the current times the internal resistance of the second battery. Again, because the second battery is being discharged and it is supplying power to the rest of the circuit. Okay? So we can now execute our solution. So the first thing for letter A, of course, we need to solve for the total current. Okay? So we just slightly modify our formula for the total current in a loop to be as follows. Okay? So since the two batteries are connected, series opposing, then the numerator will be the difference between the EMFs. Then the denominator will be the sum of the two internal resistances and the external resistance. Okay? So substituting the values, okay, we obtain total current of 1 ampere. Okay? Then we can now solve for uh, the terminal voltages of the individual batteries, and it is pretty straightforward. So we just use these two formulas. Okay? So for letter B, so we just use this formula. Okay? Then we substitute the current here, and then E1 and R1 are both given. So we just substitute them. Okay? Then the terminal voltage is 6.25 volts. Okay? Next, for letter C, we just use this second formula. Okay? So it's given here. Okay? So the terminal voltage is of the second battery will be 11.5 volts. Okay? Then finally, for letter D, okay, so how do we determine the terminal voltage of the two batteries in series? Okay? So in this case, okay, we just subtract the terminal voltages of the individual batteries since they are connected series opposing. Okay? So simply, the larger terminal voltage minus the smaller terminal voltage. Okay? So it's just equal to 11.5 minus 6.25. So it's equal to 5.25 volts. Okay? So again, before I end this lecture video, let's try to evaluate our answer, and also we try to find alternative solutions for this problem. Okay? So first, here. So the terminal voltage of the second battery is 11.5 volts, and since it is the second battery is discharging or supplying power, so it must be less than E2, which is 12 volts. So yeah, it makes sense. Okay. Next, for the first battery, so it is being charged, so its terminal voltage must be greater than E1. Okay. Okay. Again, it is satisfied. Okay. Then for letter D, okay, the terminal voltage of the two batteries in series, we can solve it in another way. Okay. So how? So looking at the figure here, we can replace again the two batteries in series using the concepts in lecture 5. We replace these two batteries by its equivalent EMF and internal resistance. So therefore, for example, we can have E sub t and R sub t. Okay? So the R sub t, so meaning these two batteries, okay, can be replaced as, okay, we have internal resistance R sub t, okay, in series with an EMF. Okay, again the EMF, since E2 is greater than E1, okay, but they are connected series opposing, so we have the direction as dictated by E sub 2. Okay, we have here E sub t. Okay, and then we just connect it to capital R. Okay, so R sub t will just be equal to R1 plus R2. Okay, and then of course the E sub t will just be equal to E2 minus E1. Okay, so uh, okay, so we can now solve actually letter A, okay, to solve for the total current or total supply current. Okay, then we can also use that to solve letter D more conveniently. Okay, so the terminal voltage of the two batteries in series will just be equal to the terminal voltage of the equivalent battery. Okay, in particular, uh, it will just be E2 minus E1 and then uh, minus the uh, minus IT times RT. Okay, so meaning for this value, okay, can also be obtained using E sub t minus, okay, IT times R. So I leave it up to you to verify that this value is the same, will be equal to 5.25 volts. Okay, so that's the first one. And then some notes. Okay, so for series opposing connection is usually used when we want to charge, okay, one battery, for example, using another source. So one typical application is a car battery, in which we use one battery in a car to charge another battery in another car. Okay, so we can draw its equivalent circuit as similar to that in the previous slide. Then for series aiding, okay, series aiding, for example, series resistance here, then battery connected to another battery, but we have the same polarity. Okay, so we have the plus. Okay, this first battery will try to establish a current in this direction, and for the second battery connected in series, we also try to force a current in that direction. So this connection is series aiding. Okay, so it is used to obtain a higher value of EMF. Okay, so the equivalent EMF will just be the sum of the two EMFs, and it is usually used in our gadgets or toys, where we use multiple batteries, for example multiple AA batteries, each with open circuit voltage of around 1.5 volts to obtain higher voltages. For example, for 4 batteries, then we obtain an EMF of 6 volts and so on. Okay, So this ends the solution to sample problem number 4.